So continuing to the intersymbol interference, so you can find out there are some symbols that have been marked as 1 and 0. So the receipt pulse and the slicer now extend to about 4-bit periods. So if the 4-bit has overlapped each other, here you can see there is an overlap here. There is an overlap here. There is an overlap here. So these are the things that are known as intersymbol interference. The actual received signal is the superposition of the individual pulses. So there is a superposition. How you can decide that will be 1 or 0, right? So if you want to find out 1, you need to have an amplitude here that is not below to 1. It's closer to 1. So that is the intersymbol interference. After that, here the intersymbol interference has been again derived. So there is a non-zero values at ideal sample instance corresponding with the transmission of binary zeros. Clearly, the case in making decisions is data dependent. So there are after getting smeared about the interference between these two. So sometimes it will be seen like that. Both can be you can say it can be just smeared down. You can say smeared down. Total output. The decision threshold, that is apart from the decision threshold, it is difficult to find out which symbol is right or wrong. So in part of the intersymbol interference, as you can see here, there are some overlappings that make the symbol right now like in that fashion. Decision threshold. So individual pulses are there, but the received signal is this. So that's not correct to say because of the intersymbol interference. As you can see, some intersymbol interference here too. There is a decision threshold that is sending a longer data sequence here. The following receipt form as slicer input. So you can get the slicer input and also showing the individual pulses decision threshold like that. So there are certain blocks that have been jam packed or getting the interference right there. Now go through to the eye diagrams. What are known as the eye diagrams? The worst case error performance is in noise can be obtained by calculating the worst case ISI over all possible combinations of input symbols. A convenient way of measuring ISI is the eye diagram. So practically this is done by displaying the YT on scope, which is triggered using the symbol clock. So there is a symbol clock there. If you find out the eye diagram, okay, that's a symbol clock. So overlaid pulses from the different symbol periods will lead to crisscross display with an eye in the middle. So that's the eye diagram. So here is the example of the RC response. That is one kind of eye diagram. Here you can see the eye diagram. Why it is called eye diagram? There is H that has been formed. This look like an eye. That is the eye diagram. It's a decision threshold. So different type of values with the optimum sample instances are there. That makes the diagram with an eye. So that is the eye diagram. Now, size of the eye diagram, age, eye height determines the probability of making incorrect decisions. That means we have to find out the incorrect decisions. The previous one is the RC diagram, RC responses. The instant at which the maximum eye opening occurs gives the sampling time TD. The width of the eye indicates the resilience to symbol timing errors. That means if the width is greater than that, so the resilience of symbol timing errors is greater than, that means it is resistance, so you will get less what can I say, error. For MRI transmission there will be M1 eyes, just one eyes, everything to one. So that's the thing. How much array transmission there is? Two arrays, the two eye diagrams will be created. If it is one, there is one diagram, eye diagram will be created. The generation of a representative eye assumes the use of random data symbols. So we can get the random data signals and analyze them. For simple channel pulse shapes with binary symbols, the eye diagram may be constructed manually by finding the worst case 1 and worst case 0, superimposing the two. So the Nyquist pulse shaping is just providing the It's impossible. It's possible to eliminate ISI, that's intersymbol interference, at the sampling instance by ensuring that the received pulse satisfies the Nyquist pulse shaping criterion. So, if there is a shaping criterion, if we didn't find out the impulse function at the point, that is, the delay time will be zero. If the delay time is zero, as you can see, if the delay time changes, the two signals overlaps each other and there is error occurs. So in the slicer input is like that. You can say the initial value of the impulse signal 80 and all other are the same. So when you find the initial signal, even you know that if the received pulse is such that there is an impulse. So if it's n equal to 0, equal to 1, if it's not 0, equal to 0. So that can be happen. Okay. So as you can see, that's the Nyquist pulse shaping. What is the Nyquist pulse? Is yn equal to an plus bn, and so ISI is avoided. When you get the value, when you just put the value here, the h0, you find the h0. The h0 is 1, so you get just an, right? So just put the value here. You can see there that is the an plus bn. So no another function that can overlap. So this condition is only achieved if and only if that's the frequency, and you know 1 by t is also frequency. There is sample time period. So there is the value of k. That's the decider value. That's minus infinity to plus infinity. You will get the total time period out of it. So that is the condition that's only achieved to improve ISI. There is a pulse spectrum repeated at the intervals of the simple rate sums to a constant value t for all frequencies. So that's the thing. So the pulse spectrum repeated at intervals of the simple rate sums to a constant value t for all frequencies. Now, what is the Nyquist pulse shaping? So here you can see there is a Nyquist pulse shaping, right? So Nyquist pulse shaping, it includes a pulse shaping with, you have to avoid this kind of superimposed or overlapping situation to get the better results. Just shape the pulse. Okay, so why we will do that? The sample HT with a train of delta pulses at times kt. There is a train of pulses, like as you can see. There is a train of pulses right there. Right there, a train of pulses, as you can see. So why it is important? So when you just make the impulse at kt times, so you can write it the equation like that. That's the H is the masking, the filtering equation. So consequently, the spectrum HST is like that. Just make the time domain to the frequency domain. So that is the Fourier analysis that are there. And after, remember, for 0 ISI, if you want to attain the 0 ISI, you have to have impulse function, the unity impulse function, right at the signal, what you can say, that is propagation. So another thing is that if HST, the masking will be the delta t, as you can see in the previous one, the spectrum will be 1 and you can get the HS omega to 1. So substituting the f omega by twice pi, that gives the Nyquist pulse. Just substitute the f with the omega. As you know, omega is equal to twice pi here. Just get the omega by 2, and replacing the value, you will get the total period of time, and the pulse shaping took place like that. Here you can see, if we use the pulse shaping technique, here the impulse sections, whether it's not attached, it is 0, and if it is attached, the value is 1 right there. You can see here, and there is no such kind of thing, such kind of place that will overlap. It's there clearly. The repeated spirit would sum to a constant value. So that is the Nyquist pulse shaping, that we can really reduce the intersymbol interference. So what are the another part of the Nyquist cost shaping? So these are the things.